Hey everybody, Mr. Wader here, and today we are going to be going over cephalopods and marine adaptation related to them. So to start, we need to know what a cephalopod is. Cephalopod is any member of the molluscan class Cephalopoda. Mollusks are things like snails as well, but we're talking about the cephalopods, which are squids, octopuses. Yes, that's the plural, it's not octopi. I checked. That's because octopus is apparently from Greek, not Latin. And that matters because it would be octopi if it was Latin. But anyways, it's not. Cuttlefish, nautiluses, and prehistoric ammonites. So ammonites are fossils, if you're going to see them today, because they have all gone extinct. But the rest of those still exist. And I feel like you could probably figure out the order in which they evolved, at least to a small degree, because you can see which ones look closer to the ammonites. And you look at the nautilus, and the nautilus looks basically just like an ammonite. And that's going in order. Squid is on the left there, then it's an octopus, then in the middle you've got a cuttlefish, then the nautilus, and then the ammonite. All of these have a shell, but most of them are internal. You'll notice two of them have external shells. That'd be the ammonite and the nautilus, and that's why you can pretty quickly tell that those are the most closely related in terms of the evolutionary ordering. And then finally they have beaks. If you've ever had the misfortune of seeing how an octopus or a cuttlefish or a squid eats, it's pretty terrifying actually. They have a beak. The cuttlefish beak looks a lot like a parrot beak actually. It's kind of funny. But their mouth is underneath their face, so to speak. Just in case you've never seen these before, I found this picture online, and I think it does a pretty good job of showing you the different ones that exist. First difference between an arm and a tentacle is that an arm has lots of suckers, and a tentacle only has them at the end, or it doesn't have them at all. And if you've had calamari, I feel like you can figure out which of those it would be. Anyways, you've got the different nautiluses over there. They list the different types of squids. Spirulina are actually kind of weird looking. Cuttlefish is my favorite out of these. They are amazing at camouflage, which we'll get to. Then there's the octopus, which has 8 arms, hence octo. And then on the right side there, you've got finned octopuses, squids, vampire squids, which have things called filaments, which we're not going to go into detail, but they are in fact different than tentacles and arms. And then on the bottom there, you've got belemnoidea. It's noidea, not no idea, which is kind of funny. Those are also extinct. And you've got the ammonites and the plectronoceridae, which are the ancestors to the cephalopods. And it says a cuttle snail with a question mark there because it's kind of hard to put together the evolutionary lineage for things that are extinct like that based off of only a fossil record. But they look like a snail that had started the process of forming a shell in a similar fashion to an ammonite. Hence the whole a cuttle snail question mark. All right, so this guy right here is technically a geologist, but he did a TED talk on some really cool adaptations of cephalopods.
But I want to jump up to shallow water now and look at some creatures that are positively amazing. The cephalopods, headfoots. As a kid, I knew them as calamari mostly, but this is an octopus. This is a work of Dr. Roger Hanlon at the Marine Biology. And just fascinating how cephalopods can, with their eyes, incredible eyes, sense their surrounding, look at light, look at patterns. Here's an octopus moving across the reef, finds a spot to settle down, curls up, and then disappears into the background. Tough thing to do. In the next bit, we're going to see a couple of squid. These are squid. Now, males, when they fight, if they're really aggressive, they turn white. And these two males are fighting. They do it by bouncing their butts together, which is an interesting concept. Now, here's a male on the left and a female on the right. And now the male has managed to split his coloration so that the female only always sees the kinder, gentler squid in him. And the males on the We're going to see it again. Let's take a look at it again. Watch the coloration. White on the right, brown on the left. He takes a step back, so he's keeping off the other males by splitting his body, and he comes up on the other side. Bingo. Now, I'm told that's not just a squid phenomenon with males, but I don't know if that's Cuttlefish, I love cuttlefish. This is a giant Australian cuttlefish, and there he is, his droopy little eyes up here. But they could do pretty amazing things too. Here we're going to see one backing into a crevice, and watch his tentacles. He just pulls them in, makes them look just like algae. Disappears right into the background. Positively amazing. Here's two males fighting. Once again, they're smart enough, these cephalopods, they know not to hurt each other, but look at the patterns that they can do with their skin. Okay? Just an amazing thing. Here's an octopus. Sometimes they don't want to be seen when they move because predators can see them. And here's this guy actually can make himself look like a rock, and looking at this environment can actually slide across the bottom using the waves and the shadows so he can't be seen. He blends right into his motion blends right into the background. The moving rock trick. So we're learning lots new from the shallow water, still exploring that deep, learning lots from the shallow water. There's a good reason why. I mean, the shallow water is full of predators. Here's a barracuda. And if you're an octopus or a cephalopod, you need to really understand how to use your surroundings to hide. In the next scene, you're going to see a nice coral bottom. And you see that an octopus would stand out very easily there if you couldn't use your camouflage, use your skin to change color and texture. Here's some algae in the foreground and an octopus. Isn't that amazing? Now Roger spooked him, so he took off, a cloud of ink, lands, and when he lands, the octopus says, "Look, I've been seen, best thing to do is get as big as I can get." That big brown makes his eye spot very big, so he's bluffing. Let's do it backwards. I thought he was joking when he first showed it to me. I thought it was all graphics. So here it is in reverse. Watch the skin color, watch the skin texture. Just an amazing animal, can change color and texture to match the surroundings. Watch him blend right into this algae. 1, 2, 3. And now he's gone, and so am I. Thank you very much.
Okay, so there's a lot that just happened in that video there. You were able to see camouflage, ink. You didn't see shells, but I want to really quickly just refer back to those for a sec. And then jet propulsion.
Cuttlefish, octopuses, and squid have an almost otherworldly ability to control their appearance. What makes it possible are these spots. They're called chromatophores. They're like tiny water balloons filled with colored pigment. When the balloons expand, you see more pigment, more color. When they contract, the color shrinks to a tiny dot. The overall effect can be really dramatic, and for good reason. These animals don't have protective external shells. They're unarmored, naked, and they aren't great swimmers either. Camouflage is their best defense. They have to be good at it. Octopuses can change their body position and the pattern on their skin to match rock or coral. Octopuses and cuttlefish can even change the texture of their skin to throw off predators, become bumpier and more rock-like. But squid often live in the open ocean. How do you blend in when there's nothing except water to blend into? They do it by changing the way light bounces off their skin. They can actually adjust how iridescent their skin is using light-reflecting cells called iridophores. They can mimic the way sunlight filters down from the surface, hide in plain sight. So how do they control all this color change? Is it voluntary or some kind of built-in reflex? That's what researchers at Stanford University wanted to know. So they anesthetized the squid and then snipped the nerve from the brain that controls the chromatophores, but only on one side of the animal. The brain essentially couldn't send messages to the tiny muscles that control those chromatophores anymore, almost like turning off a light switch. But after a few days, they noticed something strange. The chromatophores began blinking again, even though they were no longer getting signals from the brain. So what does this mean? Well, what it suggests is that color change might be a bit like breathing is for humans, something we can either choose to do or do automatically, only even cooler. Because unlike breathing, color change requires an awareness of your surroundings. And in these animals, that awareness is spread throughout the skin, as if the skin itself could see. It would be as if your skin knew what color the walls were, even with your eyes closed. For a soft and squishy creature trying to stay alive in a very big ocean, it's a pretty spectacular defense.
Okay, so here is an abridged explanation of how these work. Basically, chromatophores are a kind of cell, and they have the ability to control the constriction of those. So basically, you can either relax it or contract it. And when it's contracted, you get the color, and when it's relaxed, you get a lack of color. If you can control the pattern of relaxed and contracted chromatophores, you can change the pattern that's visible to what's around you. And if you can see the pattern of what's around you, then you can copy that pattern by relaxing and contracting the chromatophores in such a way that it mimics that pattern. So that last bit was a little bit on ink. I just thought it was fascinating that the ink is made out of melanin and mucus, and that the melanin is the same stuff that's in our skin. Crazy. So the last thing on the list is jet propulsion. I skipped over the shells a little bit because I just wanted to show you how the shell is related to the jet propulsion and the rest of it. So the ink, jet propulsion aspect, and shell component are all internal for most cephalopods. You can see on the left there a snail, and on the bottom of that same picture, an early mollusk, and then on the right of it a clam, which is a bivalve. So those are all three different offshoots evolutionarily of mollusks. So you've got snails, bivalves, and squids. The snail and the clam have external shells, and the squid has an internal shell that's basically in the head cap there. And its shell is a protective layer that covers its digestive tract, and it can, depending on the shape and type of squid or cephalopod, it can also help protect some of the other organs a little bit. For some it's larger, for some it's smaller, but the moral of the story is it's on the inside, it's not on the outside, so they're still squishy. They also have a mantle, which is a cavity where it allows for the influx and outflux of water and nutrients, stuff like that. For jet propulsion, cephalopods actually use the fact that there's a bunch of musculature in there, and they can pull water in. Normally, that's useful because it gets to the gills. If you notice, the mantle cavity has the gills right there. Same with the snail and the clams. But once they take the water in, they have to get rid of it too. And since it's full of muscle, it does a trick similar to what a heart does when it pushes the blood out, and it just constricts and then just fires the water out. And as it does that, it creates a really big change in pressure, which pushes it. Thank you, Newton, for your third law, action-reaction. This is the exact same thing that they do to get rid of ink. They shoot ink from the same basic area there. They have a siphon right here, and they shoot the water out there. It is also the exact same place that they shoot the ink out from, which makes sense if you think about it, because they have an ink sac that stores the ink, and then they have mucus from within their body, and they mix the two on the way out, and it makes sense that you would make mucus in an area that's full of liquid already, like seawater. All right, so your assignment for today: what are 5 things you learned about cephalopods? What is one possible future technology you think cephalopods' adaptations might impact? And that could be literally anything, but a big hint is that they make ink and they can do crazy things with colors. So if you're looking for an area to look into, something involving color is probably a good place to go. And then finally, which is your favorite? I personally think cuttlefish are really cool because their mimicry abilities are insane, but all of them are really cool. So whichever one you like the best.